Hi everyone, this video is going to cover the notes for lesson 2, and this is going to be on pages 6 through 8 in your pink packet. So please make sure you're taking notes in the packet as you're watching the video. So the big idea we're going to start off with in calculus is this idea of limits. And for this lesson, there's really 3 things that we're going to need to be able to do by the end of the lesson. So we have 3 learning targets. So the first is I can write a limit statement using correct notation that references a given function. So I really want to kind of focus on the verbs here. So the first one, in addition to understanding what a limit is, we're going to need to be able to write those statements. And I really want to emphasize here this correct notation. Notation is going to be a big deal in calculus, so I want us really early on to get into good habits about being specific about our notation. Our second target is I can estimate a one-sided and or a two-sided limit given the graph of a function. So the key idea here is this idea of estimating. So when we learn ideas in calculus, typically first we'll start by learning a technique to estimate an answer, and then we'll get more sophisticated techniques for finding the exact answer. So with limits, we're going to be estimating today given the graph of a function. So we're just going to be working with graphs for today. And then our third target is I can justify why a limit does not exist at a point using limit statements when necessary. So here the big idea is to be able to justify our answers. So in calculus, a lot of times we're not going to just have to give the answer, but support or justify why that answer is true, and you'll be learning specific ways to do that as we go through this lesson. All right, so getting into the notes here, the first piece is just a review really of the Desmos activity that we did yesterday, reviewing piecewise functions. So these graphs are the same as the ones that were in the activity. And we started off just by evaluating a function at certain x values. So this is notation that we're all really familiar with. This f of 2 is asking me for the function value when x is equal to 2. So in parentheses, obviously we're referencing there an x value. So for the first one, when x is 2, I'm going to find the value of that function, which is right here, and the y value then is 4. So that function value or y value is 4. In our second graph, we're still looking at an x value of 2. I need to find the function value. Now here, this graph looks a little different. But remember, the function is defined only where that circle is closed. So again, that happens when y is 4. For our last one, again, f of 2, we've got x equals 2 here. Now, I first run into this open circle, but I know that's not that function value there. I have to keep going looking for that closed circle. And again, that happens at a y value of 4. So the big idea from yesterday was that although f of 2 is equal to 4, for all of the functions shown in the graph above, each of the graphs look very different. And so that's why in calculus we have this idea of a limit. Knowing that f of 2 is 4 doesn't tell us much about the behavior of that graph around x equals 2. And so we need a better way to describe the actual behavior near that x value, and that's what a limit is going to do for us. It's going to help us better describe that behavior. All right, so for our limit, again, a limit is going to be the y value that a function approaches as x approaches a specific number. That limit's going to tell us where the function is heading. So regardless of the actual function value at a point, it's going to tell us kind of where's that function heading or what's its behavior. So here you can see our notation, and we'll look at that more specifically in a minute. But for right now, I want to write how we would say this. So we would say the limit as x approaches c of f of x is L. So going back to the notation, so this c here, that c is going to be an x value. So it tells me the x value that I'm approaching. This f of x, that's just the name of our function. And it's super important whenever we write a limit statement, it has to reference a function. So in this case, we're calling it f of x. And then L, get my purple here. L is the y value or the limit. So the limit is L, and that's always a y value, as we had highlighted above. So whenever we're looking for a limit, we're looking for a y value. Now, when we consider limits, we really have to talk about one-sided limits. So we're going to talk about this idea of a left side limit and a right side limit. So first, let's go ahead and focus on this notation. When I look at this notation here, I notice this little minus sign. And so when we see that, here's what we say. This we would say the limit as x approaches to, from, in this case, the left. So that minus sign indicates that I'm approaching to from the left. So when we have our graph, here's what we would be thinking. I'm going to find where x is 2, and you would not have to draw this in your work unless it helps you. I just want to draw it to illustrate the point here. So that dotted line is where x is equal to 2. And I know over here is the left side of 2, and over here is the right side of 2. So if I'm approaching 2 from the left, it means I'm getting closer and closer to 2, but I'm starting on that left-hand side. So if I start traveling from the left along this function, as I get closer and closer to 2, I can see that my y value is approaching 4. So my limit value here would be 4. Now, if we look at the other example, this is our right-sided limit. I see a little plus there in the notation. So this we would read the limit, you can probably guess this already, as x approaches to from the right. And so again, going back to my graph, here's where x, that line x equals 2. There's a left side of that line and a right side. And in this case, I'm approaching from the right side. So if I get my pointer back here, means I'm traveling here, I'm getting closer and closer to x is equal to 2. And in this case, I can see that y value actually corresponds to 5. So in this case, we notice that our left side limit and our right side limit don't agree because those pieces of the function have some different behavior. So here's how the one-sided limits kind of connect up to this bigger idea of a two-sided limit. So a two-sided limit is when we look at both one-sided limits. And again, if you look at this notation, this is the notation that we had started with. So the big idea here is a two-sided limit only exists if our left-sided limit is equal to the right-sided limit. So I'm going to make a note here. This notation is telling me I only have a two-sided limit if the left-sided limit is equal to the right side limit. So let's look at a couple examples. So scenario 1 here. Now you can see in my notation, I don't have that plus or minus, I just have x approaches 2. So that tells me I'm looking at a two-sided limit, and I need to determine what that limit is. So in order to figure out the value of a two-sided limit, remember I need to consider both the left-handed limit and the right-handed limit, or right side limit. So let's look at our left-sided limit, and I'll use my pointer again. So as I approach 2 from the left, as I get closer and closer to 2, I can see that corresponding y value is 3. So my left-sided limit is 3. As I approach from the right side and I follow my function, as I get closer and closer to 2, I can see my limit is also 3. So in this case, my left-sided and my right-sided limit are both 3, so the two-sided limit is 3. Now, one thing I want to point out, even though it wasn't asked here, if we think about the actual function value, f of 2 is actually 4. So what we notice is that limit is not always going to be equal to the function value. Remember that behavior is not always determined by that function value. All right, now in scenario 2, again, looking at my notation really carefully, I can see that we're again being asked to find a two-sided limit. So I need to compare, again, the limit as x approaches 2 from the left, and I need to compare that to the limit as x approaches 2 from the right. So in this case, as I approach, sorry about that. As I approach from, I keep scrolling the screen. As I approach from the left, as I get closer and closer to 2, my function is getting closer and closer to 4. So my left-sided limit is 4. The right side, as I approach from the right, I'm getting closer and closer to 2, but from the right, my function is getting closer and closer to a y value of 5. So in this case, my left-sided limit is different from my right-sided limit, which tells me that the two-sided limit does not exist, and we use DNE to represent that. Now, here's a case where we need to think about that third target, about how we justify our answer. So in this case, it's not enough to say that it doesn't exist. We have to explain why. And to do that, we're just going to go back to this definition that said in order for the two-sided limit to exist, the left side and the right side had to agree. In this case, we don't, so we would say it does not exist because, and we would just use our limit notation to say that the left side, the limit as x approaches 2 from the left of f of x, is not equal to the right-sided limit, the limit as x approaches 2 from the right of f of x. And that would be our justification. So I'm just going to make a note there that what we just wrote here, that's going to be the justification for why that limit does not exist. All right, so to kind of wrap up the video here, we're going to go through some limit problems. These are basic limit problems that you'll see some more of in the practice that we do in class. And these typically make good multiple choice questions on the AP exam. So let's see, we're using our graph, and again, we're just evaluating these limits using the graph. So the first one, I have the limit as x approaches -4 from the left. We can see in our notation, this minus sign is telling me that I'm approaching from the left. So -4 is right here. So if I'm approaching from the left of -4, I can see my y value is getting closer and closer to 0, and that's my limit value. In my next one, I have approaching -4 from the right, so another one-sided limit. So as I approach -4, this time from the right side, as I approach -4, my limit, my y value again is 0. So now in number 3, you can see based on the notation, now I'm being asked for the two-sided limit here. So I need to compare the left side and the right side, and I can see from problems 1 and 2, those are both 0, so the two-sided limit is also 0. All right, for number 4, now I have x approaching -2 from the left. So this one we've got to be a little bit careful here. I'm going to pick a new color, maybe my pink. So -2 from the left means I'm traveling actually along this piece of the function. I'm coming up to -2 from the left. I can see my y value, or my limit, is equal to 2. Now, as I approach -2 from the right, that means I'm traveling along this curve here. So as I approach -2 from the right, I'm approaching a y value of 0. So in number 6, when I'm asked for that two-sided limit, I need to compare the left and the right-hand side. Since those do not exist, again, we would say the two-sided limit does not exist because the limit as x approaches -2 from the left is not equal to the limit as x approaches -2 from the right. And notice in my notation there, right, that first target, we have to make sure we're including the name of that function in our notation. All right, let's keep going here. So now we're looking around 4. So from the left, the right, and then the two-sided. And so you'll notice something interesting here. At x equals 4, we've got this vertical asymptote here. So if I were to look at my function approaching from the left, you can see this is just going to be that y value is just going to keep getting smaller and smaller. It's not approaching a specific value. So in that case, we would say that limit is equal to -infinity. Now, on the other hand, when I'm approaching from the right side of 4, you can see just the opposite is happening. That y value is just going to keep increasing without bound. And so in that case, our limit's going to be +infinity. So now when it comes to the two-sided limit, since those one-sideds don't agree, again, this would be the case where that two-sided limit does not exist because the limit as x approaches 4 from the left of f of x is not equal to the limit as x approaches 4 from the right of f of x. Okay, 3 more problems to go and then we will be done. So for number 10, now this is the limit as x approaches 1. And you can see it's not a left-hand or a right side limit, it's a two-sided limit. So I have to make sure when I'm answering this question that I'm considering both sides. So if I look around x equals 1, as I approach from the left side, so here's 1, be careful with the scale. As I approach from the left side, I can see I'm approaching a y value of 1. As I approach from the right side, I'm still approaching that y value of 1. So in this case, we do have a two-sided limit of 1. Now, in 11, this problem's a little bit different again. Now they're asking not for the limit as I approach a finite number, but for the limit as x approaches infinity. So here's what we're really talking about. If I look at my graph, when we're talking about the limit as x approaches infinity, we want to know if this graph just kept going forever and ever, what would that limit be? Well, here it looks like we're going to be approaching a horizontal asymptote at y equals 0. So in that case, our limit as x approaches infinity is going to be 0. We're going to get closer and closer to 0 as we approach that asymptote. Now for 12, when we look at the limit as x approaches -infinity, now we're really looking out here at this other end. When we're considering at infinity, we're really looking at the end behavior. So -infinity says, well, if I just kept going and going, following the curve here, you can see that our y values would just be getting bigger and bigger. They're not really leveling off to a certain value. So our limit here would just be infinity. All right, so that is the basics of limits. I know that was a lot of information. So again, make sure you've got your notes. Make a note of any questions that you have, and we'll start off class next time by addressing those questions. All right, thanks. See you back in class.